Welcome to The Explainer. Today, we're pulling back the curtain on a bit of digital magic you use every single day, probably without even thinking about it. We're talking about the art of making files smaller.
So let's just jump right into the big question. How is it possible to shrink a file, but keep it absolutely perfect? I mean, it seems impossible, right? It's like folding a piece of paper to make it smaller, but then being able to unfold it later with not a single crease. But get this. This magic trick is the foundation of so much of our digital world. To really get how this works, you have to know there are two main flavors of compression. First, you've got lossy compression. Think about your JPEGs or MP3s. It's really clever. It throws away tiny bits of data our eyes and ears probably won't even miss, and in return, you get these huge savings in file size. But today, we're talking about the other side of the coin, lossless compression. This is for when every single bit matters. We're talking text documents, computer code, stuff like that. The goal here isn't just a good copy, it's a perfect bit-for-bit reconstruction. All right, here's our game plan. We're going to look at why we can do this in the first place, then dive into a really smart coding system, see exactly how that code gets built, and then we'll uncover the one surprising limit to it all. Okay, so what's the secret sauce here? What makes lossless compression even possible? How can you say the exact same thing, but with fewer bits? Well, the key isn't magic. It's a simple word, redundancy. You see, it turns out that almost all the data we create, from the words I'm speaking to the code running your apps, it's not random at all. It is full of patterns and repetitions, and these predictable bits are exactly what a clever algorithm can latch onto to describe the same information more efficiently. Just look at this simple string. It's super obvious, right? The letter A shows up way more than anything else. This uneven distribution, this statistical redundancy, that's the gold mine that compression algorithms are digging for.
So, okay, we know there are patterns. How do we actually use that to our advantage? Well, this brings us to a really brilliant and surprisingly elegant idea from a guy named David Huffman, who actually came up with it while he was still a grad student.
You know, the standard way we represent text, using something like ASCII, is what's called a fixed-length code. Every character, whether it's a super common letter like E or a rare one like Z, gets the same amount of space, say 8 bits. It's simple, but it's not very efficient. Huffman's big idea was to totally ditch this one-size-fits-all approach. He asked, why not create a custom variable-length code, a code where the characters that show up all the time get really short codes, and the rare ones get longer codes. Makes sense, right? But hang on, this creates a pretty big potential problem. Let's say the code for A is 0, and the code for C is 0, 1. If you get a stream of bits that starts with 0, 1, what is it? Is it an A followed by something else, or is it just the letter C? That kind of ambiguity would be a total deal breaker. The solution is a really clever rule known as a prefix-free code. And this slide just lays it out perfectly. Look at that bad code on the right. 0 is the beginning, the prefix, of 0, 0. That's what causes all the confusion. But now look at the good code on the left. No code for a letter starts with the entire code of another letter. It's brilliant. It means that when you're reading the bits, the second you've matched a complete code, you know exactly what that character is. There is zero confusion.
So how do you come up with these perfect, unambiguous codes? Well, it's not just guesswork. It's a surprisingly simple and elegant algorithm that builds a special structure called a Huffman tree. And here's the cool part. The very way this tree is built guarantees that the codes will be prefix-free.
The process is just like what you see here. You start with your list of characters and how often they appear. Then you find the 2 least frequent characters and you merge them together under a new parent node. And you just keep doing that over and over. You take the 2 lightest things on your list, combine them, and put the new node back in. You repeat this until everything is merged into one single tree. Then, to get the codes, you just trace the path from the very top, the root, down to each letter. And the genius part? Because every character is at the very end of a branch, a leaf node, it's impossible for its code to be the start of anyone else's. The tree structure itself enforces the rule for us. So if we go back to our example string, all those characters that only appeared once are at the bottom of our priority list. The algorithm would grab 2 of them, say C and D, and merge them. Then it would grab E and F and do the same. It literally builds the tree from the bottom up, which guarantees that the rarest letters get buried the deepest, giving them the longest paths and the longest codes. And voila, here's the final result for our little string. After the tree is all built, we get our new codes. And look at that, just like we wanted. Our super frequent A gets the shortest code possible, a single bit. Meanwhile, the rare characters like C and D get the longest ones. This custom-tailored code is going to be way more compact for our specific text than a generic 8-bit code ever could be.
Okay, so this whole thing works beautifully on data that has patterns. But that brings up a really fascinating question. What happens when there are no patterns to find? And this leads us to a really mind-bending but mathematically proven truth. It is impossible to create a lossless compression algorithm that is guaranteed to shrink every single possible file. It just can't be done. Some files are fundamentally unshrinkable.
We call these incompressible strings. The best way to think about it is a file filled with truly random data, like the results of a million coin flips. There are no patterns, no repetitions, no characters that show up more than others. It's missing the one thing, redundancy, that these algorithms need to work their magic. In fact, if you try to compress a file like this, you'll almost certainly make it bigger, because on top of the original data, you have to add the compression instructions too.
And the proof for this is actually super elegant. It's called the pigeonhole principle. Think about it like this. Let's take all the possible files that are exactly 8 bits long, okay? There are 256 of them. Now let's count up all the possible files that are shorter than that. So 7 bits, 6 bits, all the way down to 0. If you add all those possibilities together, you only get 255. You see the problem? You can't fit 256 different items into only 255 available shorter slots. It's just a mathematical impossibility. At least one of those original files has to end up the same size or even get longer. So this leaves us with a really final, fascinating thought to chew on. This whole field of lossless compression is based on one thing: finding patterns. That means the absolute best you can possibly compress a file is, in a way, a perfect measure of its own internal randomness. An unshrinkable file, a truly random string of bits, is a glimpse into the nature of pure information itself, information with absolutely no pattern or predictability. Pretty wild when you think about it.